Have you ever imagined what it would be like to stand on the surface of Pluto and gaze up at ice towers as tall as the Empire State Building? Picture methane ice spires, sharp as knives, stretching 500 meters into the alien sky, structures so massive they dwarf anything we've ever seen on Earth. Today we're embarking on an incredible journey to the edge of our solar system, where NASA's New Horizons mission has revealed one of the most extraordinary discoveries in planetary science. These aren't just frozen sculptures, they're geological monuments that have completely transformed our understanding of this distant world. What we once thought was a dead, frozen ball of ice has revealed itself as a dynamic world with weather patterns, atmospheric cycles, and geological processes that challenge everything we thought we knew about planetary evolution. If you're enjoying this cosmic journey, go ahead and give it a like. It really helps us explore more mysteries of the universe together. But here's the sobering reality. These methane ice skyscrapers, called penitentes, shouldn't exist according to our old models of the outer solar system. Their discovery tells a story of atmospheric dynamics, climate cycles, and geological processes operating on timescales that make human history look like the blink of an eye. When New Horizons flew within 7,800 miles of Pluto on July 14, 2015, its cameras captured something that left scientists speechless. In a region called Tartarus Dorsa, they saw row after row of sharp-edged ridges separated by deep valleys, creating a landscape that looked like enormous knife blades had been thrust up from the surface. Can you imagine the moment when mission scientists first saw these images? The structures spanned thousands of square kilometers, reaching heights comparable to New York's tallest buildings. Initially termed bladed terrain, these formations presented a mystery that would take years to solve. The breakthrough came from Dr. John Moores of York University in Canada. Working with his team, including postgraduate Dr. Christina Smith and researchers from Johns Hopkins University and NASA, Moores developed sophisticated computer simulations that combined atmospheric models with the physics of evaporating ices. Their work, published in Nature in 2017, definitively identified these formations as penitentes, but on a scale that defied imagination. The technical specifications are absolutely staggering. These methane ice spires reach approximately 500 meters tall. That's over 1,600 feet, roughly the height of One World Trade Center. They're separated by distances of 3 to 5 kilometers, and here's the mind-blowing part: they may cover up to 60% of Pluto's equatorial region. Unlike Earth's water ice penitentes that form over just a few months, Pluto's structures have been growing for tens of millions of years. They advance at a glacial pace of approximately 1 centimeter per 248-year orbital cycle. That's right, in one complete orbit of Pluto around the Sun, these towers grow about as much as your fingernail grows in a month. The formation process itself is a masterpiece of physics operating under extreme conditions. It all begins with tiny topographic variations, bumps and dips of just a few tens of meters on Pluto's surface. When sunlight hits these areas, something remarkable happens. Solar radiation penetrates the methane ice and begins bouncing around inside, like light trapped in a crystal. This internal reflection concentrates energy in specific spots, creating focused heating zones. Where the energy concentrates, the methane ice doesn't melt. Remember, we're talking about temperatures of minus 230 degrees Celsius here. Instead, it sublimes directly from solid to vapor. But why does this create towers instead of just evaporating the ice evenly? The answer lies in Pluto's bizarre atmospheric conditions. With an atmospheric pressure about 100,000 times weaker than Earth's, molecular collisions are incredibly rare. Gas molecules can travel up to 87 meters before bumping into another molecule. That's like a single person wandering alone in a football stadium. This creates what scientists call a long mean free path, and it's crucial for the spacing we see between the penitentes. As the concentrated solar energy carves out bowl-shaped depressions, the geometry becomes self-reinforcing. The growing spires cast shadows that protect some areas while concentrating even more sunlight into the valleys. The process requires extraordinarily stable conditions, wind speeds of 1 meter per second or less, maintained not for days or years, but for millions of years. It's like balancing a house of cards in slow motion for longer than the entire history of human civilization. Now you might be wondering, how do Pluto's ice giants compare to the penitentes we find here on Earth? Well, it's like comparing a child's sandcastle to a medieval fortress. Earth's penitentes, found in the high Andes Mountains above 4,000 meters, reach maximum heights of about 5 meters, that's 16 feet. They're made of water, ice, and snow, forming during the summer months through a combination of melting and sublimation. Pluto's methane monsters are literally 100 times taller. If you stood at the base of one and looked up, you'd be craning your neck to see something as tall as the Eiffel Tower. The spacing between them is so vast you could land a spacecraft in the valleys. Each gap stretches 3 to 5 kilometers, roughly the distance from Battery Park to Central Park in Manhattan. But the differences go deeper than just size. Earth's penitentes need temperatures that dance above and below freezing, creating a daily cycle of melting and refreezing. Pluto's formations exist in perpetual deep freeze, where methane ice transforms directly to gas without ever becoming liquid. It's a completely alien process, operating under conditions we can barely imagine. What does the existence of these massive structures tell us about Pluto's climate history? This is where things get really fascinating. These formations are like geological time capsules, recording atmospheric conditions stretching back tens of millions of years. For these penitentes to form and survive, Pluto must have maintained stable atmospheric conditions over vast timescales. This isn't a dead world. It's a planet with complex climate cycles tied to its 248-year orbit and its chaotic axial tilt of 122.5 degrees. That extreme tilt creates seasons unlike anything else in the solar system, with polar days and nights lasting 124 Earth years. Recent observations have shown something troubling. Pluto's atmospheric pressure has declined by 20% since 2016. This suggests these magnificent formations might be relics from a time when Pluto had a denser atmosphere, possibly during periods when it was closer to the Sun in its elliptical orbit. The methane cycle on Pluto operates completely differently from any precipitation system on Earth. Instead of rain or snow falling from the sky, methane gas rises to higher altitudes and condenses directly onto mountain peaks and elevated surfaces. It's like frost forming on your window, but happening on a planetary scale over millions of years. Since the initial flyby, continued analysis of New Horizons data has revealed even more extraordinary features. In 2022, scientists confirmed the existence of cryovolcanoes, ice volcanoes named Wright Mons and Picard Mons. These features suggest geological activity within the last 200 million years, hinting that Pluto might harbor a liquid water ocean beneath its frozen surface. But wait, it gets even more incredible. The James Webb Space Telescope has been studying Pluto from 2022 to 2025, and what it's found has blown scientists' minds. JWST discovered that Pluto's atmospheric haze controls its climate in ways completely unlike any other world we know. The haze particles both heat and cool the atmosphere simultaneously, creating an entirely new type of planetary climate system. This haze explains a long-standing mystery: why Pluto's upper atmosphere is 30 degrees Celsius colder than our models predicted. It's like discovering that Earth's clouds not only bring rain, but also control our planet's thermostat in ways we never imagined. Recent studies suggest these methane ice spikes extend far beyond what New Horizons directly photographed. Based on surface roughness analysis, they might cover approximately 60% of Pluto's entire equatorial region. That makes them among the most extensive geological features on the entire dwarf planet. How do weather systems work on a world so far from the Sun? Pluto's atmospheric circulation is nothing like Earth's. Instead of our familiar patterns of high and low pressure systems, Pluto has north-south flows driven by nitrogen sublimation in the north and condensation in the south. This creates a planetary-scale conveyor belt of gases. The atmosphere might be thin, but it's remarkably active. Katabatic winds, cold, dense air flowing downslope under gravity, dominate the surface. These winds maintain the calm conditions necessary for penitent formation, rarely exceeding 1 to 2 meters per second. It's like a gentle breeze that's been blowing steadily for millions of years. Between 1988 and 2015, something strange happened. Pluto's atmospheric pressure tripled, despite the planet moving farther from the Sun. This demonstrates extreme thermal inertia, where the surface continues releasing stored heat long after peak warming. Current models predict that up to half of Pluto's atmosphere might freeze out completely as it continues its journey away from the Sun. The discovery of these methane giants has profound implications for our understanding of the entire solar system. This marks the first definitive proof that penitentes can form on worlds beyond Earth, opening up the possibility of similar features throughout the cosmos. Research now suggests that Jupiter's moon Europa might host similar formations beneath its icy shell. Radar data shows surface roughness patterns consistent with penitente-like structures. Scientists are also investigating whether Mars could develop these features under specific conditions. The process might be common wherever we find the right combination of volatile ices and atmospheric conditions. Think about what this means for our understanding of distant worlds. We used to imagine the outer solar system as a collection of frozen, unchanging spheres. Now we know these are dynamic worlds with weather, geology, and processes that operate on timescales that humble our human perspective. The structures also make us reconsider the potential for complex chemistry in unexpected places. On Earth, penitentes in the Andes host communities of extremophile organisms, life that thrives in conditions we once thought impossible. While Pluto's extreme cold rules out life as we know it, the discovery of active geological processes expands our definition of what makes a world alive in the geological sense. These discoveries remind us that the universe still holds countless surprises. Every time we think we understand how planets work, worlds like Pluto show us there's so much more to learn. These 500-meter ice towers stand as monuments to nature's ability to create beauty and complexity in the most unlikely places. As we look toward future missions to the outer solar system, what other secrets might be waiting? Could there be even taller penitentes on worlds we haven't explored yet? Might similar processes create entirely different types of formations under conditions we haven't yet imagined? The story of Pluto's transformation from a point of light to a complex, dynamic world with skyscraper-sized ice formations shows us the power of exploration and human curiosity. John Moores and his team didn't just solve a mystery, they opened a new chapter in our understanding of planetary science. These methane ice giants will continue growing at their incredibly slow pace, just 1 centimeter every 248 years. Long after our civilization has passed, they'll still be reaching toward Pluto's hazy skies, eternal monuments to the strange and wonderful processes that shape worlds at the edge of our solar system. What do you think about these incredible formations? Have they changed how you imagine the outer reaches of our solar system? Share your thoughts in the comments below. I'd love to hear what aspects of Pluto's geology fascinate you most. And if you want to explore more cosmic mysteries and mind-blowing discoveries from across the universe, hit that subscribe button and join us on our next adventure into the unknown. Until then, keep looking up and wondering what other impossible worlds might be waiting out there in the darkness.